see what's going on? It's recording. Your lack of focus. Let's get focused. Okay. 12.6. To sketch planes and to find equations of planes. These are actually a lot easier than do a line in 3 space. Remember, a line in 2 space is pretty easy because there are 2 easy points to plot all the time. What are the 2 easy points to plot when you're doing a line?
0.
On the blackboard. The
X-intercept,
which is something comma 0, and the y-intercept,
which is
0 comma something, right? So you can just plug x equals 0 in the equation, plug y equals 0. Now with planes, we can find these points where the plane intercepts the axes, and that's what we're going to focus on. So first let's look at recalling 2x plus 3y equals 12 is the equation in 2D, right? It's a line. It's definitely a line in 2D. And remember how you plot this? How do I get the x-intercept?
6.
By setting y equal to 0, you get the x-intercept. You put your little hand over this. 2x equals 12, x equals 6. 2, 3, 4, 5, 6. Are we good with that?
I said 4. For the y.
Yes, now you set x equal to 0.
Let the record show.
Cover that up. 3y equals 12, so y equals 4. So there you go. I'm going to get my fanciest line here. Right there. There we go. Recall that? Because you now extend that idea into 3 dimensions, but the thing is we get something very different. What is 2x plus 3y plus 4z equals 12 in 3D? So let's get out a 3D graph paper. There's more over there if you need some. 2x plus 3y plus 4z equals 12 in 3D. Well, you can do the intercept idea again, but this is the leap you've got to make. It was easy enough when you had 2 variables to pick a number for one variable and then solve for the other. If I let x equals 0, do you see how that leaves me with 3y plus 4z equals 12? Yeah. It doesn't tell me anything. No. So you actually set 2 of the variables equal to 0 to get a nice point, to get an intercept point. This 3y plus 4z equals 12 is actually called the yz trace. It's when x equals 0, you're basically in the yz plane, and 3y plus 4z equals 12 would be the line we'd get in the yz plane where this plane, the big plane, intersects the yz. What we're going to do, though, is just set a second variable equal to 0. Set both x and y equal to 0. Now your equation becomes much simpler, right? Now you've got 4z equals 12. By setting x equal to 0 and y equal to 0, it results in 4z equals 12 and z equals 3. Just writing down the process there, because sometimes when you look over your notes, you might wonder, well, what happened there? Well, we picked the x and y to be 0 first, and then force z to be 3. Now, that's a much easier point to plot than something like we did yesterday with 2, 3, 5. You don't have to come up with a big box. You can just go right on the z-axis there with 0, 0, 3. So that's 0, 0, 3, right? That's one point on this thing. I haven't really established what it is yet. Now what?
0 for 0.
Put 0 in for x and z. And what do we get for y then?
4.
Yeah, y equals 4. Right? Cover up these two, you get 3y equals 12, y equals 4. So that's 1, 2, 3, 4. So this is the point 0, 4, 0. And then finally, let's set y and z equal to 0, and that forces x to be 6. 1, 2, 3, 4, 5. Oh, went a little over. That's okay. Here's 6, 0, 0. Now, are those in a line?
No.
Are you sure?
In a plane.
Maybe you just got the wrong perspective. No, clearly these aren't collinear because you imagine these two in the xy plane, and this point 0, 0, 3 is totally off the xy plane. This point, this is called, like this is called the xy trace. It's what you get when you set z equal to 0 and you get 2x plus 3y equals 12. It's basically a line entirely in the xy plane. And you can do the trace on all the other ones too. Connecting these two, this is the yz trace. You get it by setting x equal to 0, and you get 3y plus 4z equals 12. And then finally, of course, you got a trace over here as well. Now, you don't need to know the names of all those traces. The key graphing skill I want you to have out of this is how do we graph this plane? By graphing the 3 intercepts. Not just 2 intercepts now, it's 3 dimensions. So you have an x, a y, and a z intercept. And the tricky part is setting 2 of the variables equal to 0 to figure out that 3rd variable. Okay? Now, where's the plane itself? Can you see it now? Yeah. Is it the triangle?
No.
Right. The triangle is just the stuff in that positive octave. So what we could do is, the thing is, if I were to shade on forever, it wouldn't look like much. If I start shading, it goes on infinitely all these directions, I'm going to cover up the whole space, and I really don't get any idea of perspective. Now we can at least see where it's cutting through the first octave, so you can get an idea of the pitch of the plane. So, before you get all panicky about, you can make all these complicated graphs planes, these are the 2 skills. You should know how to plot a point in 3 space with either of those 2 ideas we talked about, the box or the arrows. And you should know how to plot a plane. And this thing turns out being a plane. It's not a line anymore. How do we do a line in 3 space?
It would be, you just have 1 to 0.
How did we do the x-axis yesterday? We looked at the intersection of the xz plane and the xy plane. So we said the x-axis is y equals 0 and z equals 0. Well, yeah. Y equals 0 and z equals 0 gave us the point on the x-axis. The whole x-axis is the intersection of those 2 planes. Well, we don't want to define our lines as an intersection of 2 planes all the time. Instead, we came up with lines in 3 space.
You do the Oompa Loompa!
No, how do you describe a line in 3 space?
Trace.
With a vector equation, right?
Yeah, vector
A
equation.
point plus t times a direction vector. That'll give you a line in 2 space, in 3 space, in 4 space, in any number of dimensions. Okay? Because if we take this standard sort of linear form, which kind of speaks line to me, right? But basically the linear equation, we take all the variables to the first power. If I keep doing that in higher and higher dimensions, the shape is going to keep changing. It's always going to be 1 less than the dimension. Just like 2x plus 3y equals 12 in 2 space is actually a 1-dimensional line. Now, when we do 2x plus 3y plus 4z equals 12 in 3 space, it's a 2-dimensional plane. So if we had 2x plus 3y plus 4z plus 18w equals 19,
Bush.
what would that look like in 4 space?
It would be 3-dimensional.
It would be a 3-dimensional space. So right now, we're just a special case of some 4-dimensional world right now. Okay?
That's so cool.
Okay.
What's the 4th dimension?
Now, these are a little trickier but important to think of in terms of what does z equals 2 look like? Well, z equals 2 will have this point clearly, right? 0, 0, 2. That has z equals 2. But you have sort of infinite freedom in the x and y directions. So I start building off in the x and the y direction, and I could actually make a plane like that. Oh, hello. There you go. You like that? I'm making a parallelogram and staying parallel to the y-axis and the x-axis. And this is, again, just part of it. We don't have the convenience of having intercepts for all 3. Z equals 2 has no x-intercept and has no y-intercept either. Because to do that, you'd have to get z to be equal to 0. And no, we're saying z equals 2. So z equals 2 is a plane parallel to the XY plane. The XY plane, what's the equation of the XY plane? Z equals 0, right? So we see that parallel idea again. If you keep the same coefficients on your variables, you can come up with a parallel plane by just changing your constant term. That's a big part of what we get to later on in graphing planes. Okay, y equals 3. Yeah, here's your 0, 3, 0. You want to go parallel to the z, parallel to the x, and then some people like to go like that, then and kind of complete their big there.
I'm confused.
Okay, draws like this.
It's parallel to the xz plane.
Okay, so now
No, it doesn't. This doesn't matter so much.
on the z, but it was parallel to x and y, so this one's on the y, but it's parallel to x and z.
I don't get what that other line in the middle is.
Just ignore that.
Well,
It's just another.
I was just going. What I did is, let's say I went here 1, 2, 3, 4, 5. This is the point what? 5, 3, 0. Remember, gotta keep y equal to 3. This is the point. Negative 5, 3, 0. How about down here?
0, 3, negative 5.
Yeah, let's say negative 5. And this is 0, 3, positive 5. Okay, so what's this point then?
Negative 5, 3, negative 5.
What do they all have? And this is then
They all have the
5, 3, 5. Yeah, they all have y equals 3, right? Okay. These, these are kind of tricky to draw because you have to come up with a parallelogram. And especially y equals x.
Oh, no.
What's this the equation of?
Is that the.
It's always been before the identity line, right? Y equals x. You drew that to, flipped over it to come up with inverse functions. So it was a line in 2 space, and it's a line here too because it's going to go through these points. 1, 1, 0, 2, 2, 0, 3, 3, 0, 1, 1, 0.
So it just goes up then?
So it's going like this.
It's a line. No, it's gonna be
It's a plane perpendicular. It's basically like the door here. Think of the XY plane as the floor, and now I'm opening up the door like this.
And then is the door pane.
Yeah, this is the XY plane down here.
What's the door now?
The door now is your Y equals X plane. So we have to show it's a plane by kind of, let's go up 4, over 4 like that. Hey, yeah, that's it.
Wait, Mr. White.
That's the plane. I forgot my yellow coloring.
The board.
Yeah. Gotta cut in there like that. Let's give you a few reference points on here. So 1, 2, 3, 4, 5. This is 5, 5, 0. And then I said, let's go up 4. This is 0, 0, 4. This is 5, 5, 4. This is 0, 0, 0. What do all these have in common? They don't have a common x or y coordinate. They always y equals x at all. Okay. So y equals x is the equation of a plane again. Not a line. There's the 4th dimension test weight. You're getting me dizzy now.
Wait, what? Oh, the new thing?
Okay, now, that's fun, visualizing all that, but the key skill in this chapter is can you write the equations of planes? What do you need? And if you have an equation plane, can you do that quick sketch and find the x, y, and z intercepts? Now, we create the equation of a plane by actually coming up with a vector perpendicular to the plane, which just seems really counterintuitive because you're used to coming up with a vector in the direction of the line to come up with a vector equation of the line. And you're also used to doing this for lines in 2 space, right? What's the key concept you need to know about the line? The slope. Thing is, does a plane have slope? The slope can change so much because it can kind of pitch this way and this way. I think you
This way
airline
and this way.
pilots think of that as the yaw or something like that.
Fatty.
You got all sorts of different pitches and so forth. It's not just your plane is pitched up and down this way, it could be going like this. Right? So, let's review what we did in 2D. How does the vector 2, 3 relate to 2x plus 3y equals 12? Well, let's check out your xy's again. If x is 0, y is 4. If y is 0, x is 6. So we go through 6, 0, and 0, 4. Okay? So there's the equation of the line. That's the graph of the line. But now let's look at the vector 2, 3. Over 2 and up 3.
Perpendicular.
It's perpendicular. It's perpendicular.
The light is still.
The coefficients on the variables give you something perpendicular to the thing.
That's really cool.
And that's what makes vectors so handy as we go into other dimensions. We can count on this coefficient, all the coefficients on the variables, creating a vector which is perpendicular to the thing we're trying to graph. In 2D, it's perpendicular to the line. In 3D, it's going to be perpendicular to the plane. How can this possibly work? Well, a little review of geometry.
No.
If a line's perpendicular to a plane, here's line L and here's plane M, then that same line M is perpendicular. Every line passing through the foot of L. No, I'm sorry. If a line M is perpendicular to a plane, let me call this M. The line is M. We've got this plane here. If M is perpendicular to the plane, it's got to be perpendicular to every line of the plane that passes through the foot of M. Remember, the foot is where the line hits the plane? It's called the foot because we stand on planes all day. Keeps us from tipping over. Right? And there's your feet. Okay? Did you try this with your feet now if you're standing up? See how I'm twisting my ankles? So I'm not just perpendicular to any old line. Right? I'm perpendicular to any line in the plane that goes through my foot. I'm not perpendicular to the line going through your foot over there. I'm not perpendicular. Perpendicular implies the dot product will be 0 and the two lines have to have a common point of intersection. These, my forearms, are not perpendicular right now. Their direction vectors are perpendicular, but technically the lines themselves are not perpendicular because they don't cross. If you're going to call two lines perpendicular in 3 space, they have to cross. Okay. So, here's a line, right? And sometimes we make it perpendicular by sort of making my little corner there. Notice how that looks like almost like a parallelogram? So when I shift my perspective like this, I should actually draw my little house and pool corner that way to give that 3D effect. See that trick? Yeah, I'm an artiste.
Art teachers.
They made a movie about me. It's going to win an Academy Award. Now with vectors, we can look at the vector AN, perpendicular to a plane containing 3 points A, B, and C. So if I draw this vector AB, it's going to be perpendicular to that. AC will be perpendicular to that. Or AP will be perpendicular to that as well. AP. So, remember how we vector equations of lines in 3 space? How did that go? How do you do a vector of equation line in 3 space? What do you need?
The coefficient of thing.
A direction vector and any point. So you take the point plus t times the direction vector. Now you can generate all the points on the line. So this is actually a trick using a vector equation of a plane. And if I ask for a vector equation of a plane, all you have to do is this. You say an dot AP equals 0. Because that guarantees then, this means that an will be perpendicular to AP, right?
So basically you're doing the same thing. You're acting as though that plane you're working with is a line, but because it's in 3 space, it really is a plane.
Right, you generate a whole plane then. So if I have a vector, I've got an infinite number of vectors perpendicular to it. But if I look at all of them, they'll all lie in the same directional plane. Okay? You might think, oh, isn't this vector up here perpendicular? Well, that direct vector is parallel to this vector. Right? Okay. Now we're going to turn this into our Cartesian equation because we want to show how we come up with that xyz equation. So if A is a fixed point, x naught, y naught, z naught, let P be any point in the plane, x, y, z. So this is x, y, z. This is x naught, y naught, z naught, a point in the plane. Then AN will be a vector perpendicular to the plane. So we're going to call this vector ABC. That's the vector, okay? Not just the point N, but the vector from A to N. That establishes our direction vector for the plane. It's called the vector normal to the plane, meaning perpendicular to the plane. Normal or perpendicular. Okay? Now, AN is ABC, right? What's AP? How do I come up with a little formula for AP? X minus x naught. There you go. See how you do that? Remember, to come up with a vector between 2 points, you have to subtract the coordinates of the points, okay? Now you do that, and that's all equal to 0. Now you do the dot product. So A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. Wow, this is looking like a complicated equation. But
Like an awesome.
distribute ax minus ax naught plus by minus by naught plus cz minus cz naught equals 0. And you get ax plus by plus cz equals all this chunk. Ax naught plus by naught plus cz naught. But this is all just a constant, right? If we're given a direction vector for the plane that's perpendicular to the plane, a normal vector of the plane, and a point in the plane, a specific point, this will all end up being a constant. And now you've got your equation. Ax plus by plus cz equals some constant d.
Oh, sorry. Why did you search equal to 0 and what is that?
Because an is always perpendicular to any line going in the plane through its flow. So the dot product has to be equal to 0. Okay?
Thank you.
So there's your formula. This is key. Ax plus by plus cz, ABC is the vector normal to the plane. And d will equal ax naught plus by naught plus cz naught. You know, I don't memorize this so much as I memorize the idea that ABC, the normal vector, will be the coefficients on x, y, and z. And then you can just plug in a point to figure out what d has to be. Okay. So digest that for a bit. I'm going to try to apply it.
Wait a minute.
While you're digesting, I'm going to pass out these. These are great. I put some notes on there. These are available for your perusal online too. I put a little note on there. I actually took 2 submissions on one problem because they forgot to switch whatever. But you don't have to know Barry. Barry. I mean, like
BA.
80 degrees. A bearing of 80 degrees means 80 degrees rotated clockwise from north. I will say that if I put a question like that. I won't expect you to know all these navigational terms. I'll be very specific on what you're measuring, what angle. Because if we talk about an angle, we've always talked about being in standard position in the plane. So if I have a problem, an application problem, I'll let you know what angle I'm talking about. Now you should know angle of elevation, angle of depression, all right?
Yeah.
Angle of elevation off the horizontal, and depression off the horizontal.
But this side, right?
Why would we do this? It depends on what I'm looking. Where's the blip?
Okay.
Like that. That's my angle of elevation. The person, the blimp looking down at me has an angle of depression that matches my angle of elevation.
Yeah.
From P,
Yeah.
A, parallel to elevation.
So like, how do you use that backwards? So you're given the Cartesian equation for the plane. How do you
Oh, okay,
find
right.
vector perpendicular?
Okay, good question. We're coming back into this now. This is not the complete story. because we have to have very specific information to come up with the equation of the plane, and it's not going to help you go backwards just yet. Right? So this whole process is designed, you see in this first example, is can you write the equation of a plane with this very specific information. By the end of the chapter, we're going to come up with all those ways you can determine a plane in geometry and figure out how to do it in coordinate geometry with vectors in 3 space. Like 3 non-collinear points determine a plane, 2 intersecting lines, 2 parallel lines. You might want to review that. Right now, we're just going to give you the vector. 3, 4, -2 is perpendicular to a plane that contains 0, 1, 2. Find the equation of the plane. So you know, we're not going to draw it out. It's too hard. But what we can do is this, say, okay, this vector is perpendicular, so that means it's going to be 3x plus 4y minus 2z equals some constant d. Now, they didn't give us the constant. But 0, 1, 2 must work in it.
Oh, yeah.
So yeah, just solve for d by putting 0 in for x, 1 in for y, and 2 in for z. And we get d equals 0. So 3x plus 4y minus 2z equals 0. I think some of you saw my little micro answer there.
You might want to put a bottom line on the z because it looks like a separate.
Yeah, thank you. Bingo. There we go. Okay. All right. Okay. That's pretty straightforward because you're given all the information you need. It's kind of like when I said, come up with the equation line that goes to the point 3, 5 and a slope of 2/3. So you just write the point slope, right?
Yeah.
Or the slope is 2/3 and the y-intercept is 5. Y equals 2/3 x plus 5. Right? It gets tricky though when the information you're given doesn't match some of the key constants. Here, in the equation of the plane, ax plus by plus cz equals d, a, b, and c, that's a very key constant. That's the vector normal to the plane. Okay, here's example 2 now. Find a Cartesian equation of the plane perpendicular to AB at its midpoint. I think I tried to do a picture of this. No, I don't think I did.
Wait, hold on. This is the equation that you just gave us a couple seconds ago. Is that the Cartesian one?
Yeah, this is called the Cartesian equation.
Okay.
From Descartes. Okay, so what do we need? We need a vector perpendicular to the plane, and we need a point in the plane. Both these are not apparently obvious right now. They're not given to you. Because we're given 2 points in space, A and B. We want the equation of the plane perpendicular to AB at its midpoint. So right away that tells you where to start. The midpoint. The midpoint. The midpoint, M, is going to be what? 1 plus 3 over 2, 0 plus -4 over 2, 2 plus 6 over 2. So we get 2, -2, 4. 2, -2, 4. Can I just divide, can I factor up 2 there?
Why would you?
That would be a different point, right? That would no longer be the midpoint. And we want to make sure we go through that point. Not through 1, -1, 2. We want to go through that point.
Algebra 1.
Okay. Now, that's great. You've got a point. What else do you need for the equation of a plane?
The ax and then like put that point in and then leave the x, y, and z and then
I think you're setting up the vector equation of the plane. You don't have to go through the proof again. All we need is a vector perpendicular to the plane.
Make the dot product equal to 0.
And it's perpendicular to line segment AB.
That's fine. Like,
So find line segment AB and think of it as a vector, and that will be your vector perpendicular to the plane. So vector AB is perpendicular to the plane. Now, you could also do AM, or MB, or BM, or MA. All those would end up being perpendicular to the plane as well.
Missing in action.
But why take a chance that we made oopsie here? Might as well use this original information. So basically, we've got a plane here, and here's A, and here's B, and we're going, shoot! Like that. what's this point right here? That's the M. So that's why I'm saying you could also do AM if you wanted to. So AB is going to be B minus A. So that's 3, negative 4, 6, minus 1, 0, 2. This step isn't necessary, but sometimes, you know, if I just write down 2, negative 4, 4, a lot of kids go, where's that come from? So, can I factor out a 2? No, people. You're so adamant before, and I agree. Now I say you could factor out a 2. Because this will be parallel to 1, negative 2, 2, won't it? And if it's parallel to this vector is still perpendicular to the plane. So for direction vectors, you can use any multiple of those direction vectors, and you're still going to be in the same direction, so it'll still serve you just as well.
For like a final answer, would you like us to simplify, like down, if we can factor something out?
Yes. And see, if you didn't do the step here, you're eventually going to have to do it later.
Yeah.
And I'll show you, I'll prove to you both ways. Now, if we did the step here, now we can say, okay, so 1x plus negative 2y plus 2z equals some unknown d. So you see how I put the components of the normal vector become the coefficients of your plane equation.
So would you use the midpoint to figure out the
Yes. Definitely want to use the midpoint. In this case, don't use A or B, because those aren't in the plane we're interested in. We're interested in the plane perpendicular and passing through the midpoint of AB. So it's kind of like a perpendicular bisecting plane of AB. So let's use M, which is 2, negative 2, 4. So I get 2 plus negative 2 times negative 2 plus 2 times 4 equals D. So that's 2 and 4 and 12. I think I did something wrong there.
2 and 4 and 8.
No, that's 18, right?
Well, 2 times 4 is 12.
That's not a 7.
2 times 4.
Yeah.
The 12 at the bottom. 12 at the bottom is an
8, yes, thank you. I was doing some advanced adding.
You were already thinking ahead.
So it's 14. D equals 14. And so that's your equation of the plane.
Wait, how did you do the 2 times
X minus 2y plus 2z equals 14. Okay, Joey? Got it? Okay. Now, what if we used 2, negative 4, 4 as the perpendicular vector? Well, then you'd have 2x minus 4y plus 4z equals d. You'd plug in m again, 2, negative 2, 4. And so you'd have twice 2 minus 4 times negative 2 plus 4 times 4 equals d. 4 and 8 and 16 equals d. Looks like 28 to me. And you end up with 2x minus 4y plus 4z equals 28. Hear me now and for all time. This is not an acceptable answer, okay? And now it's recorded, okay? So you can't come back to me on the test and go, oh, Mr. White, really? Really? Yes, I'll say really, yes. Because this is supposed to be an ease for somebody else to come up with more points in the plane, right?
Exactly.
You might as well say 200x minus 400y plus 400z equals 2800, okay?
It's essentially the same.
And then I'm supposed to accept it. No.
It's essentially the same thing.
Yes, they're equivalent equations, but one is in good form. Okay, can you guess the alternate approach, Tom?
No, why? Oh, you create one of them octahedrons.
No, I'm not going to make an octahedron. Okay? But we could talk about this, though. I know they don't look the same, but you got to use your perspective, people, okay?
Oh, yeah, they are the same. Altitude, I know.
Any point in this bisecting plane should be equidistant from the endpoints. So let's call this P, some point x, y, z, in the plane that bisects the segment. So P to A must equal P to B.
Yes.
What's the distance from P to A?
X minus 1, y, z minus 2.
And then you figure out
What we're missing here?
the midpoint.
The squares? I'm not just going to square root them.
Commas.
Oh, you just gotta you're doing the
You got to square them, people. You got to square them and square root it all, and that's the distance.
Because you can just remember square radicals of root.
Can you? No, you cannot. That's right, you cannot. So, and we have the square root of PB, which is x minus 3 squared plus y minus a minus 4 squared plus z minus 6 squared. Okay? Now you might say, oh, that is clearly much more complicated, but actually it's one step, right? And it should work out to be the same.
Let's do it.
Well, go ahead, John. You can do it. On the board, yes.
Yes.
You understand it now.
Okay, so what do we do?
John is John.
And,
John,
any contributions?
John, I need to find that
Because he's a White Sox fan.
Racist.
Because he's a White Sox fan.
You are so racist.
Notice how we squared both sides right away. That's handy, right? So it doesn't deal with big square roots. Okay, and there's a plus and there's a, right?
Oh, yeah.
John, we're gonna pause it and then we'll restart again when you're all done.
Can we say flange out?
No, don't say flange out yet. And well done, John. He figured it out. As long as we get a consistent answer.
Oh, I can just write G.
Okay, fine. Okay, does that check with the other one? Yes, it does.